It's me. Hey, it is October 19th, atypically cold. It's really cold. We're in kind of a cold snap here. Anyway, I'm standing here in the water at Square Lake, and I'll give you kind of the panorama here. So this is the public access at Square Lake, and we're talking about water quality. So I just helped this gentleman head off the water to go fishing. He wants to get some crappies. But anyway, so here's the deal. Here's the thing. Here's the deal. I want you to write a one-page paper on what you think of Square Lake based on the water quality. Now, you've seen a lecture about what the water quality numbers mean, things like temperature and pH and turbidity and how those things come together. So anyway, I'm going to show you how we gather the data on a particular lake, like Square Lake, and then I'm going to have you interpret the data as to what you think about that. So first and foremost, one thing we can do at a lake is we can do a fish survey, kind of like our bird nets. Over here we have so this is a seine net, and you can see little bobbers at the top and little sinkers at the bottom. Maybe you can't see this. There's an example of a sinker right there. But we drag this. It takes two people. My wife just left, so she and I just did a pull along the shoreline, and the net forms a little cup with two people dragging it on the shoreline. Then we rush up against the shore once we've done a little pull, and the fish get caught in the net. And when the fish are caught in the net, then we can put them into a container. So this is just the result of one pull of fish. So you can see those are mostly minnows. They're in the minnow family, and they would be called cyprinids, shiner minnows. So anyway, what they represent is a bait fish for game fish. I also saw a very largemouth bass in there, which you can, these fish can help us decide what kind of a fishery it is, because they're fish that have thresholds. For instance, a bass needs a dissolved oxygen of 6 to 8, and if it fell much below that, you wouldn't have those species. So they're kind of like an indicator species. The minnows actually can tolerate some really lousy water quality conditions, but the fact there's a bunch of minnows in here lets us know there's a food base for other fish in the lake. And to be honest, this isn't very good structure for catching a whole bunch of bluegill or crappies. If we were mowing down lily pads, as we say, like we do at Lily Lake, we'd probably have a lot of crappies and bluegills and bullheads and other fish components. So let me show you a few things. I'm going to put a little bit of an angle here so you can see. This is what's known as a Secchi disc. And a Secchi disc, it's an agreed upon width, and usually with a pattern like this. And the idea is you can measure water clarity, we call that turbidity. We can measure the turbidity of a lake by lowering this Secchi disc. And when it sinks to the bottom, if it gets all the way to the bottom, that would be great. In a lot of lakes, the clarity, the point at which that disc disappears from view, we measure how much rope that is, that distance. So in some lakes, like Lily Lake in the summer, with all the algae and stuff in the water column, it disappears maybe with 2 feet, maybe 3 feet. Square Lake is notorious for having a super deep Secchi disc reading, like something around better than 11 feet. So this disc won't disappear from view until the piece of rope is over 11 feet in depth. That's really wonderful water clarity. So that's a Secchi disc reading. The other thing we can do to look at what lives in the water is we can do a plankton net, and that's what this is. So we throw this net into the water and we reel it in several times. And what's happening is every toss of this plankton net, the plankton get caught and they trickle on down the side of the net. They trickle on down and they get collected in this little vial here. And I can pour that vial into a container, bring it home and look at it under the microscope, and we'd expect to see algae, little single-celled plant critters. We call it phytoplankton, is a fancy name for it. And then we'd expect to catch some critters that eat those algae, like Daphnia. And so this gives you an idea of what is feeding those minnows we just looked at. So whole food chain concept here. Are there algae eaters that feed the minnows? And I'm sure there are. So that's another water quality test we can do. Now, it's going to be hard for you to see, but we have these LabQuest computers, and what you're seeing here is a LabQuest computer, and it's hooked up to a turbidity meter. And what we do is we take a sample of water from the lake, put it in this little vial, and this vial then goes in a machine, and we read here how there's a little beam of light that gets shot through the machine, through the water sample and back, and the amount of reflected distortion in that beam will give us a turbidity unit. And turbidity is measured in JTUs, Jackson Turbidity Units, and also NTUs, and I think NTUs are probably a little more popular. But what's weird is the scale goes from 0, which is awesome, 100% clarity, to up to 200 plus units of unclarity. So a good lake might have a turbidity of 25. So if we're talking about dissolved oxygen, you say that's excellent. But if we're talking about another parameter, it may not be so. So that's the range, let's just say 0 to 200. 0 being awesome and usually unattainable for a lake because there would be algae and other things in it. And 200 or beyond would be very, very poor water quality. I would guess chocolate milk probably has something like 400 NTUs. So we've also tested, we can test nitrate, and you'll recall that is the nitrates are part of that we call basically nutrient, and there should not be a strong nitrate test. And so our little strip here says, if we match the colors here, it shows that there are 0 nitrates in the water, and that might be a little deceiving. You see this lawn here? If they're using fertilizer on this lawn, and I doubt they are, because fertilizer is expensive and this is a county park, but if that were to wash into the water, that would be bad. It would be adding nutrient or nitrogen and phosphorus to the water. And the plants, the deal is it's hard to measure because the plants will almost immediately soak it up and put it into their plant tissues. And this is why this stuff is so dangerous. But anyway, we have a 0 reading for nitrogen, and in phosphorus, this test has been sitting out for a while. So it has gone from 0 or a pink color. It's gone from a 0 or pink color to blue because it's sat out in the air. It's oxidized. So anyway, nitrogen and phosphates 0. pH is also leached here. I try to do this as a demonstration, but we can use litmus paper, and the pH was 7, and I have a pH probe for our LabQuest, which also read 7. So that's, I'll let you decide what that all means, but a pH of 7. And then we have dissolved oxygen. So this is a dissolved oxygen probe, and it's been sitting in the water, and it runs its information. What's kind of neat is I have a switcher. I can either read in parts per million or I can read in milligrams per liter. And we got a dissolved oxygen of 11 parts per million, which is fantastic. It's also a little artificial because it's so cold out. The water is cold, it easily holds more dissolved oxygen. But with one flip of the switch, I can go percent saturation, and I'm sure the saturation level will be over 90% saturated. The water is pretty much full of dissolved oxygen. And so those are some of the parameters that we've measured here, which is a pretty grand array. And then lastly, this is a cool one. Oh, don't go fall in the water, it'll sink. So this last test is how we measure poop. And as I was walking along the beach, I saw a bunch of goose poop. Probably shouldn't eat it. But we have this machine here. It's called a Buchner filter, or it's also called a vacuum filtration technique. And here's how this works. We take a piece of sterile filter paper and put it on here. And this is magnetized. And we take exactly 100 mils of water, lake water, which is about that much. And we're going to hook it up to this. I'm going to show you how this works. The idea is we drag a known quantity of water across a piece of filter paper. So I'm going to create a vacuum by using this handle. And if you look carefully, you might be able to see water dripping out of that vacuum filter. And I'm dragging the water across the filter. So what will happen is impurities, sand, silt, algae, anything that's in the water making it cloudy will get caught in that filter. And what's really cool is the bacteria are also getting caught in that filter. Still pumping, still dripping. So I've just about got all the water across my piece of filter paper. So the bacteria that land in the paper, I'm gonna put it in a little petri dish and I'm gonna give it a specially designed, it's about $1 a sample, but a specially designed piece of nutrient on top of the filter paper. Put it in a petri dish, let it sit for 24 hours at room temperature, and any fish or crayfish poop will have little blue colonies that they'll form. Any human poop will be little red colonies. So let me show you how that works. So I've got, all I care about is my filter paper. This is a little petri dish. Take the top off like this. Take my filter paper off. Not sure if you heard that. So now I've got, you can see it's a, you might be able to see it's a little bit yellow in coloration compared to the edges that were trapped in the petri dish. And now this is kind of the cool part. This is a little glass ampule with the growth, the bacteria growth media that'll turn different colors depending on who pooped it, whether it's a human poop or whether it's fish poop or crayfish poop, whatever. So I would hope that we'd have wildlife poop in the lake because we'd want fish and things in the lake. I'd also hope that we don't have human poop. So like, this is just, this blue container breaks the glass. Okay.